So last section we're going to look at is 5.5. Okay, it's a little bit more on logs. And in this section, we're going to focus mainly on drawing. Okay, a little bit of sketching by hand, some sketching on the calculator. What are the two logs that we know that the calculator can do for us?
Log 10 and
E.
Yeah.
Is ln.
So the two bases that the calculator can do is log. Like if I do something like that, which base did I use there?
Log 10.
Base 10.
Base 10.
Yep. And if I type in something like that,
E.
I used log with a base of e. So if we have something that is not a base 10 or a base e, I'm going to show you how you can type it in. All right? And this will work on any scientific calculator as long as it has a log. Can you just move that over a little bit? I get nervous. Thanks. That's how you can do it. So it's log base b of x, where the b would be a number and the x would be a number. There's two ways you can do it. So let's actually do one as we look at the formula. So let's say I ask you to find the log of 5 and the base is 3. Is base 3 one of the logs that the calculator can do? No. So one way that you can type it in is the common log of the argument. So start with that number. So type in log 5 divided by the log of the base. So in this case, log 3 divided by log 3. And we get about 1.46. Now, the other way you can do the change of base formula is just with ln's. You can take the ln of the argument, so ln of 5, and divide by ln 3. And you get exactly the same answer. So that's called the change of base formula. You take the log of the argument and you divide by the log of the base. It is important when you do it that you close your parenthesis, because when you press ln 5, it's going to open one. When you're done with that, you need to close it yourself. Okay, if you don't close it and you do something like this, ln 5 divided by ln 3, that's wrong. Now you've got an ln inside another ln. Okay? And you get a completely different answer. All right, now that number that we just found, 1.46, that number is a what? Because we got it by pressing log.
Exponent.
It's an exponent. Okay, what's it an exponent on? Well, think about this for a second. We don't know what this equals. Well, let's pretend we don't. Let's say it equals x. What's the base there? 3. What's the exponent?
5.
No, logarithm always equals the exponent. So logarithm, the base is 3, x is the exponent, and what goes on the other side? 5. So the number that we just found, that 1.46497, that's what you raise 3 to get 5. Let's try it. 3 raised to the 1.46497. And it gives me 4.99998 because I rounded it. But that's what that number is. So you're solving for an exponent when you use this formula. All right. Let's try, I think I might have another one. Let's try log base 8 of 13. How would you type that one in on the calculator?
Log 13.
So log 13.
Parenthesis divided by log 8.
Yep. It's not critical you close the parenthesis at the end because there's nothing else coming after it in this case. So that would be about 1.233. So it should be approximate. Good. Question on that one? All right, so now we're going to look at graphing a log, but we're going to need that formula to do it. How come I need that formula we just went over to graph that log?
Because you can't graph log 3, you need an actual number to graph.
Can you say that again? I can't what?
You need like an actual number in order to graph, or what?
No, when you're graphing, you need an x in there, like y equals mx plus b. So you need to have an x. But why can't I type that in without the formula I just showed you?
Log
It has
3
a
is not
base of
coordinated.
3.
It has a base of 3. Okay? You cannot type in a base 3. So how would we rewrite it so we can type it in?
Log.
Yep,
Log x divided by log 3.
divided by log 3. So the first step to graphing that and finding the domain and range is to rewrite it so you can type it in. All right, so let's put that in under y equals. Okay, we've got log x divided by log 3. Right, and let's do zoom 6. Now, when we graph it, we have to be a little bit careful when we look at the graph.
Does that one go straight down, just too steep?
Yeah, it goes straight down. That is not a good picture of how it should look. Right? It should, and I'm not sure if we already talked about that, but it should keep coming down
How do we know,
like that.
how do we know it goes straight down?
You have to know based on what you typed in. So when you graph a log functions always have one of those. Does anybody remember what you call that red dotted line?
Asymptote.
It's an asymptote. Yep. Log functions always have a vertical asymptote. The other way you can kind of tell is if I erase the part I did in blue, where does it look like that one stopped?
2.
It looks like it stopped at -2. Okay. Go on your calculator and zoom in. And watch what happens if you zoom in near -2. Where does it look like it stops now? Looks like it stops now at -3. It looks a little different. The more you keep zooming in, you're going to see that this just keeps going down forever. It just gets to be too steep, so the calculator can't do it. Right? So when you draw a log function, there should always be a part that goes down forever and a part that goes one way. In this case, it goes to the right forever. Okay, so let's look at the domain. So domain is how far left and right that graph in blue goes. Does that graph in blue go to the left forever?
No.
No, then all of a sudden it stops somewhere. Where does the graph in blue stop going to the left? At 0. Does it ever reach 0?
No.
No, it just gets very close to it, but it never reaches it. What symbol do I use when I get close to a number but I don't reach it?
The parentheses.
Parenthesis. Now that's how far left it goes. How far right does it go?
Infinity.
Infinity. Do we ever reach that?
No.
No. So that's the domain of this log function, 0 to infinity. Okay. How about the range? We want to look at how far down and how far up. Does it look like it goes down forever?
Yes.
Yes. It will go down forever.
Just never approaching 0.
Yep, as you approach 0, the y value goes down forever.
So would it be 0? So it'd be 0 going up.
And how high does it look like the blue one goes?
Infinity.
Forever.
Just
Forever.
slow.
Yeah, it's very slow, but it's basically going to kind of do something like that. Maybe even flatter than that. It's going to keep going up forever, very slowly, extremely slowly.
Wait, but I thought there was like an asymptote.
There is. There's a vertical asymptote at that red dotted line.
But not a horizontal asymptote.
There's not a horizontal asymptote. No. No. If there was a horizontal asymptote, then yeah, it wouldn't keep going up, it would have to level off. But this one doesn't.
So for log functions, do they ever have a horizontal asymptote?
No, that's the range for every single log function that we study. It's always negative infinity to infinity.
So we're just gonna have to find the domain.
Yeah, the domain can change, because if I did something like, let's just draw a basic log. Let me do log of x minus 5. Look at how this one looks. This part comes down right here. And this part just keeps going that way. How far to the left does it look like that one goes?
Infinity. Wait, what are you talking?
Well, infinity is to
Like
the
it looks
left.
like it stops at -5.
So it goes all the way to -5, which is right
Oh,
there?
5, positive 5.
Positive 5, yeah. So in this one, the domain would be from positive 5 to infinity. Right? The range is still negative infinity to infinity. So you can't change the range. But you can change the domain if you slide the function left or right. Yeah. Okay. Any question on that one? All right. Okay, so let's look at this one. Transformations. So this is probably either the 4th or 5th time we've looked at transformations. All of the transformations that we know from the previous sections, the A, B, C, D, it works exactly the same for logs. A and B are inside the function. So does anybody remember when you have numbers inside, are those the horizontal transformations or the vertical? Horizontal. Yeah, horizontal are the ones inside. A is adding, or it could be subtracting. B is multiplying. What kind of transformation is it when you add? A stretch or a shift?
Stretch.
Which way is it? Stretch or shift?
Shift right.
It's a shift.
Left.
I didn't ask the direction yet, but it is a shift. Yeah. So A is a horizontal shift. Now, if it is positive, which way does positive?
Left.
Positive will move it left. Yep. And negative?
Right.
To the right. Okay, how about B?
Stretch.
What kind of stretch?
Horizontal.
Yep, it's inside. Inside is always horizontal. And it is a stretch. Remember though, it is backwards. So if you had something like this, log 2x,
Maybe smaller.
that would be a stretch by 1/2. I should say horizontal stretch. Okay, so log 2x would be a horizontal stretch by 1/2. What if I had log 1/3 x?
Maybe 3.
That's a horizontal stretch by 3. Again, you might think 1/3 is a smaller number, so it makes it smaller, but it doesn't. The horizontal is always backwards. The vertical is not. Okay, let's do C. Now C and D are on the outside of the argument. So C and D are going to be what?
Vertical.
They're going to be verticals, and C is multiplication. So what kind of transformation would that be?
Stretch.
Stretch. Stretch is when you multiply. Okay, so vertical stretch. And there's nothing to write there because it's pretty much common sense. If you have 3 log x, it makes it 3 times bigger. If you have a half log x, it makes it half as big. Okay. And how about
Vertical.
D?
shift.
That's your vertical shift. positive is going to move your graph
Right.
Up,
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 and negative would move your
Down.
graph
down.
down. Yep. So that's 4 of them, A, B, C, D, but there's a total of 6. What if, we always put these kind of off to the side. What happens if B is negative? Yep, it would be a reflection. What kind of reflection? Horizontal or vertical?
Horizontal.
Horizontal, because it's B. B is in the horizontal section. Anything in this box is horizontal. So if B is negative, we get a horizontal reflection. What about if C is negative?
Be a vertical.
That's a vertical reflection. So there are your 6 transformations. A gives you 1, B could be 2, C could be 2, and D could be 1, up to 1. All right, so let's try this. So this one says, how can log base 3 of negative x be graphed from log base 3 of x? So when you are comparing 2 logs, these numbers will always match. Okay, you're not going to compare a base 3 log to a base 4 log. You're going to compare base 3 to base 3. How many transformations would it take to change that into that? Just 1. Yep, there's only 1 transformation. So let's start with the transformations. Okay. So when we look at where the negative is, and then we match it up to the chart and figure out what it's doing.
Wouldn't it be a horizontal reflection?
Yeah, think of it as like having a negative 1 in front of x. That's a horizontal reflection. Yep. Horizontal reflection. Okay, what else do they want? So that's how you would graph it. Find the domain. Let's come back to that. We'll do the domain after we sketch it on the calculator. Let's do the range. What's going to be the range of this log function?
Wouldn't it be negative infinity? Infinity.
Yeah, no matter how you flip it, reflect it, stretch it, shift it, you can never change the range because it goes up and down forever. So range is all reals. So let's sketch it. Log base 3 of negative x. Okay. How am I going to type that in? Because it is not base 10.
You're gonna do log x, no, negative x,
Log negative x.
divided by log 3.
Yep. So let's type it in, look at it, and see if we can get these other couple things. Okay, so you can tell what that negative did. Right? That's not the way that they normally curve. That reflected it. Okay, and what's not shown very well in that picture?
Going down.
Yeah, this part should just keep going down like that. Because you have a vertical asymptote right now. Okay. So now let's do our domain. Okay, does this go to the left?
Yes.
Yes.
Infinity.
Yep.
Infinity.
So it goes all the way to negative infinity.
Would it be negative infinity 0?
Yep, and it goes all the way up to, but never reaches 0. Okay, so now where is your vertical asymptote? Yeah, it's at x equals 0. Okay, the vertical asymptote is that line that it never reaches, and that line is at x equals 0. It's the value that your domain stops at, or you can view it as the one it starts at, however you want to look at it. But it's the line that the curve bends away from. That's where the vertical asymptote is. And I think that's everything they wanted: transformations, domain, range, asymptotes. Any question on that? Okay, let's try another one. This time, just describe the transformations. We don't have to do everything else. Okay, so first thing is looking at the problem that I gave you. Does it look like what I wrote on the board for the A, B, C, D chart? Not quite. Okay, we need to fix that. How would we rewrite that so it matches up exactly with what's over there?
Negative x plus 3.
Yep, log negative x plus 3. Now they want us to describe the transformations. Okay, how many transformations does this one have?
4.
2.
2, right? This one only has 2. It has the plus 3, which we're going to describe first.
Wait, how do we get from 3 minus x to negative? You just switch
We
it
just
to
flip the
sides?
Yeah, we just use the commutative property to change the order because it's not in the order that I gave you. So I'm trying to make it match exactly what's on the left side. So now go in order. Start with A, B, C, then D.
It's a horizontal shift to the left. By 3.
Shift left, how many units?
3.
3 units. Okay, you don't have to say horizontal. Left means horizontal, so that's okay. So shift left 3 units. And what about the negative in front of the x?
It's a horizontal reflection.
That's a horizontal reflection. So a normal log function will curve to the right. If you reflect it horizontally, it's going to curve to the left. It was just another transformation one to practice. Any question on that one?
No.
Okay. Okay, so now let's try a sketch. Yeah, let's do a sketch. Okay, so when you're sketching, the nice thing about logs is they only curve in one direction, so you don't need to worry about checking points in 2 directions. We just have to check one. A couple things that we do want to find though: where the graph crosses the x and the y axis. That's going to give us a couple important points. And you definitely want to find the vertical asymptote, because once you have that, you have an imaginary line that the graph is going to bend away from. So you have to find that vertical asymptote. Here's how you find the vertical asymptote if it's been moved because of a transformation. First of all, the only thing that can affect the horizontal asymptote is what's in that red box. Nothing outside that makes a difference. What kind of transformation is C? Vertical stretch. Imagine you have a line that goes up and down forever, and you stretch it to be twice as tall. How tall would it be now?
Infinite.
Still a
It's
vertical truss.
still infinitely tall. That's why stretching something vertically, when it already goes up and down forever, doesn't matter. So C has no effect on it. And if you had a line that goes up and down forever, and you slide it up 1 unit, would it look any different?
No.
No. Because it's infinitely long, so if you slide it up 1, you can't even tell that you did that. No. So D has no effect on the asymptote either. What's in that red box is the argument. That is the only thing that can affect the vertical asymptote. So to find the vertical asymptote, set the argument, that's the bx plus a, or it could be bx minus a, set that equal to 0, and solve it. Don't worry about C, don't worry about D. That has no effect on the vertical asymptote. Okay, and just a reminder of how you find intercepts, if you don't remember. To find an intercept, you need to plug in 0. Where you plug in 0 is going to control what intercept you're finding. If you plug in 0 for y, that will give you the x-intercept. If you plug in 0 for x, that'll give you the y-intercept. So we're going to try this on the next question. Okay, we'll find some intercepts, we'll find the asymptote, and then we'll do a sketch. Now, the intercepts are going to give you 2 points on your graph. So you might have something like this and like that. But you're probably going to need a third one to be able to get a good sketch. All right, so we'll usually check one more point. Usually that point, it's just limited by the size of my graph paper. So I usually pick an x value less than 10, because my graph paper doesn't go above 10. 7, 8, 9. Pick a point that's far away from the intercept.
20.
Because if you have a point here, and you already have a point here, don't pick a point like there. That doesn't really help. Pick a point further over there, so then you get a good sketch.
You can't really see where that on the bottom is going.
Oh, it's a log function, so it's just dropping straight down.
Gotcha.
Yeah. Just dropping straight down. Now, when you pick another point, since your graph only curves in one direction, you need to pick a point that is in the direction it curves. If you pick the wrong direction, this is what will happen. Go to your table. You're going to get a lot of errors for numbers. Okay, they're all going to come up as errors. And that's because this particular graph does not curve to the right. And I tried to find points going to the right. Well, I can't. It doesn't go to the right. It goes to the left. Okay, so let's try a sketch. Okay, so the first one says sketch a graph of that, and then find the domain, the range, and the asymptotes. Well, the range we should be able to do right now. What's the range?
Negative infinity, comma infinity.
Yep, that never changes. I'm not going to write that just yet, but we will in a second. Let's start with the vertical asymptote. What were the directions that I gave you to find the vertical asymptote?
I do not remember.
Do you have it in your notes?
Probably.
Something we
Set the
just wrote down in
argument-
the past 5
Set
minutes.
the argument to 0.
Set the argument equal to 0. To find the vertical asymptote, set argument equal to 0, and then solve. Okay. What's the argument in that problem?
3x plus 5.
Yep. 3x plus 5 equals 0. And my first step to get x by itself,
Subtract 5.
subtract 5.
Then you divide with 3.
And yep, divide by 3. So what is my vertical asymptote?
Negative 5/3.
Yep. As a decimal, that's about negative 1.6 repeating. It's negative 1 2/3. Okay, so now let's start with that. Okay, put a vertical line at negative 5/3, which is about negative 1.6. So right about somewhere in there. So now my graph is either going to bend to the right or it's going to bend to the left. Once we get a couple points, we'll know. Okay, let's find the y-intercept. What number do you plug in to find the y-intercept, and where do you plug it in?
X.
You're going to plug in something for x, yeah?
0.
You're going to plug in 0. We had that right up here, x and y intercept. Right. So let's do that. Plug in 0 for x. Okay, well, if I plug in 0, what's 3 times 0?
0.
0, and then plus 5.
5.
So I have 5 in the parentheses. Everything else stays the same. So it's log base 2 of 5. Well, that's great, but I don't know what that is. I need the decimal so I can graph that. How would I type that in on my calculator so I can graph
Log 5 divided by log 2.
log 5? Not on that screen though. Log 5 divided by log 2. Log 2. So that gives me a y-intercept of about 2.3. And it's just approximate. We're sketching by hand, so 1 decimal place is plenty.
I don't care, why can't you just type log 2 5?
How? Like, you tell me what to press.
Like, just write log 2 and then parentheses 5.
Like that?
Yeah.
Because that's going to give you the log of 10.
Okay.
That's 2 times 5. Yeah. So that's the log of 10. So with the calculator, this one, you got to use the change of base formula to type it in. Some calculators have a different way to do it, but not all of them do. So I show you a way that will work on any calculator, including any scientific calculator. Yeah. Okay, so we got our y-intercept. What's the other intercept I want to find?
X.
Yeah, so let's do x-intercept. Okay, for the x-intercept, plug in 0 for y. Okay. Where's the y in that equation? There is no y, but there's something that represents y.
The g of x.
Yeah, so you're going to put in a 0 right there. So 0 equals log base 2 of 3x plus 5. What format is that equation in? Log or
Log.
exponential? Yeah,
Log.
that's log. Let's change it to exponential. And it's going to become a very easy equation to solve. What is your base?
2.
2. What about your exponent?
Your exponent 0.
Logarithm always equals the exponent. And what ends up on the right side?
3x,
3x
plus
plus
5.
5.
Yeah, the argument. Okay, what is 2 to the 0 power?
0. No, 1.
1. So we get that. Okay, my next step to get x by itself,
Subtract 5.
subtract 5. And my last step,
Divide by
Divide.
3.
divide by 3.
1.66 would be.
Oh yeah, negative 4/3. You got what?
Oh, that's not right. Wait. Oh. That's a fraction.
Negative 4, so it's negative 1 1/3.
Yeah.
So it crosses the x-axis around negative 1.3. So that would be about right there. So I think we have enough information. We can tell which way is this one curving. It's curving right. Yeah. If it was curving left, you wouldn't have got any points on the right. So it's curving to the right. I need one more point over like in this area somewhere. What would be a good x value to pick?
8.
Yeah, 8. So let's plug in 8 for x. Again, that's a little bit more freedom there. You can pick whatever you want for x. If you plug in 8, what's 3 times 8?
24.
24.
24, and then plus 5?
29.
29. So that's log base 2 of 29. So log 29 divided by log 2. So when x is 8, I'm at about 4.9, almost 5. So when x is 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5. What did I say, 4.9? Okay, so right about there. Okay, now draw your curve. You don't need any more points over here because you already know what's going to happen. It's just going to drop straight down. So have this come up, curve, and kind of go like that. And that's how you sketch a log function. Okay, if you have trouble finding one of the intercepts, that's fine. You can just plot more points like we did this one. Maybe let x equal 5, 3, 1, -1. Right? You can use other points that you pick. But the intercepts are 2 usually good ones. Okay. Any question on that? Yeah.
Is the domain in range for this one?
Oh, did we do that? Nope. Let's do that. Well, we did the range.
Range is negative infinity through infinity.
Yeah. So it goes up and down forever. And the domain,
Negative 1.333.
yeah, -5/3. Yep, that's the lowest it goes.
And then the highest it goes to infinity.
And it heads to the right forever. Yep. So the domain is -5/3 to infinity. Okay. Any questions on that? All right. So last thing. So the last problem we're going to look at is a problem that more of an application of a log using the log formula to find the intensity of an earthquake on the Richter scale. So if you watch the news or you read about like an earthquake, usually they give you a number. And I say like it's a magnitude 4.3 earthquake. That's what this formula calculates. Okay, so there's 3 things that you need to know to be able to find the magnitude. The first thing you need to plug in is A. That's something that they have a device they can use to measure somehow in an earthquake. It's the amplitude of the vertical ground motion. So it's basically how much the ground is moving up and down in the earthquake. And it can be a very small amount, so it's measured in micrometers, okay, for a small earthquake. For a big earthquake, it could be a lot bigger. Okay, T is what's called the period of the wave. So when you have, it's a little harder to see in like an earthquake wave. You can see it better if you drop like a rock in a pond. You see a wave coming out from the center. Well, if you could put like a boat somewhere near where you drop the rock, like a small little boat, the boat's going to go up and down, right, as the wave hits it. How often the boat goes up, that's the period. So like, let's say the waves kept happening, like a rock kept getting dropped in the same spot in the pond. Every time the boat goes up and then up again, that's the period of the wave. So maybe the boat goes up every 3 seconds, another wave comes by and hits it. It's how often the waves are coming by the boat. They can be faster or they can be slower. Okay, and then the last thing is B, and that's a factor that accounts for the weakening of the wave. So depending on where an earthquake is, different types of soil might impact how bad the earthquake is. So if you drop something in like a pond, you see the waves spread out. And that's because all the water molecules are, think of them as very close. If you drop something in like a sandbox, you'll get a wave, but it almost stops right away. Like if you drop something big enough, you get a little crater and then it's just kind of done. It's because the sand is loosely packed, it kind of absorbs the energy more than transfers it. All right? So that's, again, something that they have instruments, they can measure all these things. Right, so you take these three things, you fill them in, and that'll give you the intensity of your earthquake. So let's try an example. Example 5. So find the magnitude. Okay, so the amplitude of the vertical ground motion is 250, and remember that's micrometers. That's what they measure it in. So it's very, very small amount. But there's other things that affect how bad the earthquake is. The period of the wave is 2 seconds. So if you think of that boat in the water, it's going up every 2 seconds. A new wave is hitting it. And B is the factor that accounts for the weakening of the wave. It's 4.25. Okay, so let's find the magnitude of the earthquake. All right, so let's start with the formula. They use R for Richter scale. What is the formula that I need to plug into?
Log A over T in parentheses plus B.
Yeah. So now it's just a matter of filling everything in. What's A in this case?
250.
And T?
2.
2. And B?
Plus 4.25.
0.25. All right, so let's type that in. What's 250 divided by 2?
125.
Okay, so I'm just going to do log of 125. And they didn't put a base on the log. So
It's 10.
we talked about that yesterday. That's base 10. So that would be an earthquake that has a magnitude of about 6.35 on the Richter scale. Okay, so homework tonight is the take-home test. It'll open at 2:40. It'll be open for a total of 90 minutes. So make sure if you do pause it, you save and exit, close it, you'll be able to go back in and the timer will pick up where it left off. If it is late, meaning if it is not done by tomorrow at 11 a.m., it would be a 0. So you have all of tonight to work on it. Tomorrow up until 11 a.m., including 1 hour that we are in class.
Okay, guys.